Hi, everyone, and welcome to our webinar today. My name is Paul Bemis, and today we're going to be trying to get a lot of stuff done in a 1 hour period of time, so it'll be challenging. We're going to talk about transient CFD simulation, cooling system failure, and also transient as it relates to electronics packaging. So first of all, let me introduce my panel. I have with me two co-presenters today, or support people with me today. One of them is Jim Delap, and Jim is with the Ansys Corporation and is responsible for the electronics cooling segment and products. And I'm going to first hand over to him today and let him talk about IcePack. The other person I have with me today is Abhishek Jean. He runs our consulting effort here at Applied Math Modeling, and I'll be relying on Abhishek to answer any questions that I may not be able to answer. He has a pretty rich background in technology, graduating from India Institute of Technology and working in the CFD, applied CFD application space for a very long time. So we have a lot of bench strength here in case we need it. Now, before we get started, a few logistics. This is being broadcast. It is also being recorded. If you have questions along the way, there is a chat box over there in your GoToMeeting panel. Just open up the questions section and type in a question. I will be reviewing those and trying to answer them as we go, but if not, I will answer them at the end. So we have slotted some time here for questions and answers, so we'd like to do that at the end. And if I can pick them up midstream, I certainly will. But we will certainly get to them all at the end. So the first thing I'm going to do is sort of position here for you. As you know, Applied Math Modeling is a partner of the Ansys Corporation. We use their technologies. We're a value-added partner. We build the product CoolSim, which is an application-specific implementation of general-purpose CFD tools used for the design and analysis of data centers. Now, we in CoolSim only expose a certain level of detail, sometimes referred to as fidelity, with respect to the individual server itself. However, the same exact technology and same exact code is used to do detailed work within the server when necessary and when appropriate. That is done by a product called IcePack. IcePack is analogous to CoolSim in that it is an application-specific implementation of a CFD tool for electronics packaging. So it is used for the development of thermal control as well as electromagnetics and other things, simulation issues, inside of things like cell phones, laptops, servers. Now, in CoolSim, we only get in, as I mentioned, to a certain level of fidelity, but I want you to know that these tools are analogous. In fact, they're compatible. The file that comes out of a CoolSim simulation is actually an input file to IcePack. We use IcePack in our simulation process. We use it for meshing, we use it for boundary condition, and then we go to the Fluent solver just like IcePack does for a full solve. So they are analogous and they are compatible. So I wanted to bring that to your attention. Now, the issue of transient inside of electronics package is similar in terms of physics that it is to the data center. It's just a different scale. It is a smaller scale, of course, and you apply more detail to it. And today we have Jim with us, and what he is going to do is he is going to show us a little bit about IcePack and how it works. And as he does that, I want you to keep in mind that everything he is going to show you is something that we could potentially expose inside of CoolSim at some point in the future. The question of how much we expose of the level of detail is a function of things like time in the day, simulation time, level of complexity, ease of use, things like that. But I want to make you aware of what's there. I've invited Jim here today to do that. Jim, I'll go ahead and turn it over to you. Thanks for coming.
Thank you, Paul. Can you see my screen in the first slide that I'm showing? Okay, great.
Yep, we all set.
Awesome. So as Paul mentioned, my name is Jim Delap. I'm an electronics product manager for Ansys, specializing in our electronics business unit. And I wanted to go over a little bit of our Ansys platform and a little bit more of IcePack as a tool in general, and then discuss some transient solutions within Ansys IcePack. Just a little bit of a background on myself. I've been with Ansys for about 18 years in various roles in application engineer on the electrical side, and most recently I've taken over as product manager for our signal integrity, power integrity, and thermal integrity products within the electronics business unit. So I'm responsible for not only electrical analysis tools, but also thermal analysis tools, one of which being Ansys IcePack, which we wanted to talk about today. And what my role is, I basically work with customers like yourself and our development team to essentially build the next generation of our products and determine what capabilities we need to drive these tools into the future and make them of more use to a lot more users. So give you a basic idea of the Ansys platform and ecosystem. Some of you may know Ansys from hopefully IcePack and working with CoolSim, but Ansys has a long history in mechanical and structural simulations. And over the years, other technologies have been acquired. So we have a firm foundation of physics solving with our structural mechanics tools, our fluid dynamics tools, as well as electromagnetics. And more recently, we've added the capability to do semiconductor chip modeling, very detailed modeling, as well as mission critical embedded software modeling, and more recently, optical systems modeling. So we've got market leaders as far as tool capabilities across a broad spectrum of physics. And on top of that, we've added a layer that will allow you to access a material database across all of these dimensions and be able to use a single combined database for that and solve everything together within one ecosystem or one environment. So we have the ability to combine that on top of our platform, whether that platform is in-house, like on a cluster system, or using cloud-based resources. So that's a little bit of background on the Ansys platform and ecosystem. The tool that we're going to be discussing today is IcePack, which uses our best-in-class Fluent CFD solver to solve electronics cooling problems. As Paul mentioned, most of these problems are in the form of electronics packages or boxes where you're combining PCBs, fans, heat sinks, blowers, things of that nature to model thermal problems combined with CFD. So we can do all sorts of conjugate heat transfer analysis, conduction, convection, radiation, and Joule heating in a steady state and transient capability, and also look at single or multiple species of fluids. Along with all of the basic capabilities, we can also do things like parametric and optimization and the generation of reduced order modeling. And IcePack as a tool is used at a variety of scales within the electronics industry, all the way from the chip level to chip and package up through boards, assemblies, and system levels. And with the partnership of tools like CoolSim, we can do things up into the data center level of abstraction. So IcePack offers the ability to go across all of these levels of scales. And within the toolset, we actually have the technology available in 3 different versions. The one on the right is the IcePack version that is most commonly used in the industry for mechanical and thermal engineers. And over the past several years, we've embarked on a mission to modernize that interface and also make the technology of CFD analysis available to other disciplines. So we've added the IcePack technology in our board tool called SI Wave to allow for DCIR Joule heating analysis on board, and give that capability to basic electrical or layout engineers. And more recently, we've added the IcePack technology into our Ansys Electronics desktop. And basically, the AEDT framework is the single cockpit that we have to look at electromagnetic simulation, thermal management, virtual compliance, all sorts of different physics are possible within the electronics desktop framework. And it allows for co-simulation between these physics and dynamically linking between things like circuits and 3D electromagnetics or electromechanics. Here are some examples of post-processing and reporting. For our transient solver, you can do the basic stuff in terms of looking at temperature, velocities, heat transfer coefficient, things of that nature on something like a detailed package, electronics box, or even maybe going up further to a rack.
Thank you, Jim. And again, if you have any questions as we go along, please type them into the chat box and I will try to answer them as we go. But let me go ahead and begin to talk about the thermal transient inside the data center. It is a little different, but again, just so you can remember, these tools are compatible. The CoolSim application effectively creates an input file for IcePack. So if someone wanted to do the detail, they could lay it out in CoolSim and then bring it into IcePack for tighter detail. But the tools are quite compatible, and everything that Jim talked about in terms of feature set could potentially be exposed inside of CoolSim if we ever needed to or wanted to. I can't imagine we would. Data center scale is quite different, but just so you know, there's a tremendous amount of headroom in terms of capability that we can draw upon as a partner if we need to. So I'm going to talk about transient simulation in data center. This does come up occasionally. It's not something that comes up a lot. We haven't exposed it directly in CoolSim yet, but CoolSim can do it. It can do a certain amount of it, and then what we do is we do outside calculations to determine what to do, and then we run the solutions inside CoolSim. So let me show you how that's done. This comes from an application that was done or a consulting job that was done recently. We went through it. I thought I'd share it with you. So first of all, let's talk about cooling unit failure in a data center. There's basically two kinds of systems you run into in data center cooling. One of them is a DX unit. DX is a direct expansion unit, and this is a one-to-one relationship between the unit in the room, which has got a compressor in it typically, and a condenser that sits out in the outside atmosphere. And it is a gas-based system that hence direct expansion. The evaporator is directly exposed to the heat in the room, not indirectly exposed. And therefore they call it direct expansion because expansion is taking place in the medium where it's trying to be cooled. And there's a one-to-one relationship between the heat exchangers. So the only thing really that you have to worry about in a DX if it's all DX, if all you have is direct expansion in the room, the CoolSim can currently handle it today with an N+1 failure mode analysis. And we automate this. You can set up N number of runs. You can say in run number 1, I want crack 1 off, and then run number 2, I want crack 2 off, etc. You can do up to 4 of those at once per simulation. It all comes back fully automated with a set of results for you. That's done. It's been done for quite some time. That works quite well. For chilled water systems, things are a little more complicated. Now, again, if you want to just understand if the air handler in the room fails, because remember in chilled water, all you have is a fan coil sitting in the room. You have N of them. And those fans sometimes fail. If you want to study a failure mode in the room, again, same exact case as before, can be done in CoolSim today. And all you do is switch off one of the units, typically in a round robin fashion until you've looked at all of them. I encourage those of you who are doing design to look at all of them because geometry makes a difference, location makes a difference. Air handlers don't all reject the same amount of heat. There's a distribution based on their physical locality in the room, and therefore, it depends on the geometry, it depends what's going on. Now, the other case is the chiller has failed, but the pumps are on the generator. This is typical. Typically, the pumps are redundant and they're on the generator. The chillers are often redundant as well. But occasionally, people will want to understand what happens if the chiller goes out or chillers go out and the pumps are still on. Now, if the pumps aren't on, we're back to a case where, and I'll show you one case where, it's just not really worth considering. But the case where the chiller failed, there is a loop there that's worth considering, a chilled water loop that's going to keep that data center cool for a period of time. People often want to know what that time is, and therefore you need to calculate the declining cooling capacity that happens as a function of time. Okay, So this is a basic model that I dragged off the internet from DOE. This isn't a bad model. This is a very basic design for a data center. And what you have here is over on the right, you have the data center, and this is a downflow system, and you've got air, cool air coming in. I guess fat arrows mean air, skinny arrows mean water. So you have the air coming down through this is a fan coil with a basically heat exchanger in it, pumping cold water through it and getting hot as it goes, and it makes the air cold through the fan, come underneath, convective cooling. These are mostly convective these days. A little bit of water, mostly convective, however, due to cost. This is the rack, so it goes in one side of the rack, comes out hot, comes back up and through. No containment in this particular design. This is what we call a convective cooled system, and that's how it works in the white space. What happens on the outside is you have the hot liquid, usually water or glycol, coming up and through the chiller. Inside the chiller, you have compression, same thing as before with a DX unit. You've got a gas in there being compressed to a high temperature, being dumped and being expanded so that the heat transfer can take place between hot and cold here to pump the heat out, done through shaft power. So you put a shaft power in there, spin it, it does compression or lift. That gets things hot. You dump it, typical Rankine cycle, that's how you do it. And then when it's hot enough to dump to the atmosphere, you usually go out through something. This is showing right here a cooling tower. This could also be a dry cooler. This could also be a reservoir. This could be many things out here, which is part of the challenge of trying to model this is what's going on out here. And then, of course, we use an evaporative cooling, latent heat of vaporization in this case to help dump heat come back in. And so you have basically two loops. These configurations can change quite a bit. For example, there could be a bypass plate and frame heat exchanger that goes around the chiller so that on certain days you can use what we call economizer mode, where you just go through the cooling tower by itself because it's cold enough outside that you don't need a chiller, you don't need to do compression. And then there's variations thereof, sometimes called trimming, where you use a little bit of the chiller, but mostly the cooling tower. Those are more complicated scenarios, but I want to point out to you that when modeling these things in a transient case, you need to know all that stuff. You need to know what's going on out there in order for you to define the problem correctly. Now, in today's case, we're going to be taking a look at this data center. This is the one that we worked on most recently. And you can see it's fairly complicated. It uses a lot of racks. They're all in different configurations in terms of location and organization and orientation. This one is using a raised floor design, so the air is blowing down like I showed you before, but it's using a ducted hot aisle return. So these translucent elements here that you see are ducts that we support inside of CoolSim. You can lay them out. And in this case, they're sucking the heat out of the hot air spaces and back down through these air handlers. These are just fan coils over here and back down through here and dumping it back out to the chiller on the outside of this room. A couple things about this data center I want to point out to you. This is a shot from CoolSim, and you'll see across the top. The CoolSim is fairly simple. It doesn't have a lot of complexity. We do that intentionally. Try to make the learning curve short because it's typically occasional users who use it. And you'll notice airflow direction here indicated by green, and you notice it's not optimal. In some cases, we have things pointing right at each other. If you take a look here, this is what we call, I'll do it over here, this is what we call classroom style, all inlets facing to the front. So this one's dumping heat into the intake of the one behind it. Not a good thing, and sucking heat out over here. So the hot air from this server has to go up over the top and go up and out. Not a perfect situation. Guess what? A lot of data centers aren't perfect. Over here, we have a similar problem. These are blown against the wall, and there's not much pulling the air out there. And there are other issues here. Classroom style, again, underneath here, if you look closely. So not an ideal configuration. I would argue that this end of the room is probably the most problematic just looking at it. No containment being used here at all, but it is what it is. And the question that the customer had in this case is, how much time do I have? Oftentimes, facilities managers want to know this because they want to be able to do two things. One, respond, get to the data center, so they need to know how long it takes them to get there to do something or be able to handle it possibly remotely. The second one is, if I'm going to pull data out of this data center because I've got critical data in it, where do I need to start pulling first? Which machines, which servers, which racks, and these are racks, are important. Final thing here is in terms of back to ice pack, I'm modeling this today as a uniform heat distribution across the front of it. This is a rack with a certain load in it. We're using a standard simple function to dump the heat across that. Now, you know, ice pack can give you much more detail. In fact, in CoolSim, you can get into much more detail. You can break that up, make it non-uniform. You can put servers in that rack. But the way that the UDF, or the user-defined function, is working here is fairly simple. It's dumping heat. There's a delta T. We're using a convective heat transfer equation to basically dump the heat across that server. The server is, or that rack. That rack is effectively a block with an inlet-outlet pair on it, a boundary condition, a pair, and we have on one side air coming in, the other side air going out. We do a function to dump the heat. That's how it works. Now, fidelity can be turned up, but of course you run into time when you do that. So for the most part, when you're looking at a data center like this, with this level of granularity, it's easiest to use a coarse level of representation for these racks and do it with average watts per rack. So in this particular design, we had 2 chillers, 2 pumps, so we had redundancy. Now the other thing you need to know is how much water is in the loop. Again, it's that primary loop we're looking at, or primary, secondary, let me be careful. It is the loop closest to the data center. It's that chilled water loop that's rotating around and keeping my data center cool that I need to know the detail on. I need to know how much water is in that loop, right? Because that's what's going to be holding the heat. So we need the details, and these details are all different for every data center. In this case, this one had 390 feet, a 4-inch diameter return and supply. It had 2-inch diameter feed lines. You have to figure out the total mass, 500 in this case, 532 gallons, and the time. We need the flow rate. How long does it take to complete the loop? In this case, it's 66 seconds, 33 to get to the chiller, 33 to get back. So that's the important information you need to know in order to do a transient study of a data center that's cooled by chilled water. Now, again, this may vary a lot. There could be a reservoir in between. Oftentimes that's done. There could be a variety of things going on that you need to know about in order to do this correctly. So you have to ask a few more questions. Now, in this case, the customer wanted to know, what if the entire thing failed? What if the chiller failed? Now, if everything fails, if the cooling system, the HVAC system fails, there's really not much to do here. I mean, the thing goes up in seconds, and I'm going to show you that in a moment. However, from a methodology point of view, in both cases, it is a transient. We're looking at temperature with respect to time, and we're trying to understand which server gets hot first and where it is in the room. And we typically use ASHRAE as the mechanism for determining the ASHRAE limits of temperature to determine when things go bad. So we're going to look at the first case. This is full system failure. This is everything that's going down. I've got the air handlers going down, the chillers going down, the cooling system goes down. It is an unusual case. Usually that does not happen. Usually at least the air handlers in the room are on some kind of backup, either battery or generator, usually backup. They're usually on a UPS. If they're not, they should be. But I'm going to do this one simply because I want to illustrate to you why this case is not one you should ask much about and is not one that is of much interest. So here we're going to assume that the fans shut down at T equals 0. Not quite true. There is a ramp. They do ramp down, but when you pull the power from an AHU, they ramp down pretty quick. So assuming it's 0 is probably fine. That time is not considerable. So we shut them off and treat them as solid boundaries and do the transient based on that with respect to time. Then we stop the simulation when a rack inlet gets to 90 degrees so that we know which one's there and which one gets hot. Otherwise, it'll just run away. We'll have thermal runaway. It will never settle and just go on and create fire. So the methodology is to, from a simulation point of view, assign the in and outlet for those air handlers as sealed, no flow exists. We pick the time step. This is important. It's transient simulation, you have to pick a time step. And if you pick it, effectively transient simulation is steady state solutions at each step. So at each time step, we solve a complete steady state solution. Now, the problem with that is if the step's too big, the solution doesn't converge because you step too far over in terms of the physics. to be able to resolve it to a steady state situation. So we pick a 0.01 in this case because we know it's going to happen pretty quick. And then we do a steady state for each one of those cases, which produces a tremendous amount of output, which again is another issue associated with transient analysis. It produces a full set of complete output for every simulation or every time step. So here's how it turned out. These are just plots of rack inlet temperatures as a function of time, and you'll notice that at 14 seconds, it's hot. And by the way, I want to point out to the audience that this is in the case where it is not contained. There are no containment being used here. These are naturally convective. The opportunity for the servers and the racks to absorb any cool air that's in the room exists. If there's containment in place, this situation gets worse because the racks can't recirculate on themselves. They can't draw any volume in the room, and you run into just a real temperature problem right away. So I wanted to point this out to you. This case, again, isn't very interesting in the sense that, that it gives you anything you need to really, you can draw from this other than you have no time. If you lose the air handlers in the room and you lose the cooling system in the room, it's game over. You have no time. You can't draw anything out in 14 seconds in terms of data. Okay, so that's that case. 9 seconds, the AHU fails. We're 9 seconds, we're getting into trouble. 14 seconds, we're over the top. Okay. I got a couple of questions coming in. I'll answer real quick. Is it possible to do a transient in a site that uses DX and dual fuel evaporators at the same time? Sure, you can. You can mix these up. They're not binary. You can mix the DX with the chilled water. But remember that DX system is going to be useless, and the chilled water system is going to have to absorb all that energy. Sure, you can do that. It's just another variation on the same point. So in this second scenario, I'm going to take a look at the case where the air handler and the pumps are operational. This is most common. This is the chiller failure. Again, we don't see a lot of chiller failures, and usually there's an N+1 on the chiller, so there's redundancy built in. But we'll do it here for you, and air handlers in this case and pumps are assuming to be operational. So here we have the same diagram. I put it up for you. Our assumptions are that the air handler is working and the pumps are working. I've got water in the loop, and it's going around here. Remember that it's this loop I'm interested in because this is what's going on. And remember that the heat from the last, just before the thing failed, is right there. So the only cool water I have to begin with at T equals 0 is what's left in this blue loop right here, which in our case ended up being 33 seconds of time. So again, we needed to know the piping. We needed to know the amount of volume. We needed to know what the medium was, in this case water, and what the temperature is. And then we have that data up here. It was 46 degrees Fahrenheit, 33 seconds. Now, sometimes these loops are very long. I have been involved with customers where these loops are long enough so that, there's minutes of time in that loop before it gets back and is hot. But in our case, it was fairly short in this particular case. So at that point, as soon as after 33, for 33 seconds, you're good. And then after that, this hot piece right here of fluid gets into that heat exchanger, and the air handler starts to lose its cooling capacity. You have the cooling capacity drops. So what we do in using a steady state solution like CoolSim is just calculate what the new cooling capacity looks like and run those simulations. Here's a plot of temperature coming out of the cooling units as a function of time when that happens. So you'll see at 33 seconds, a very big jump. Boom, the first slug of fluid hits the air handler that is no longer cool. Prior to that, you're in good shape. It runs like normal. But you see this big jump. Each one of these little lines represents one of the air handlers. We had 10 of them in this room. Now, once they hit the air handler and start to flow, you see a gradual increase in temperature. And then you hit that next slug, boom, hit it again, bang. Now this one's longer because it was the full loop as opposed to 33 seconds. I had taken the full, loop of 66 seconds to get back the water that I had just dumped before, and then I get another step, bang, and then it goes again. Here's the other set over here. You notice they're not all collinear. That's because of the piping. In other words, it's likely the hot water went to this one first, and then went to this, or the cold water went to this one first, then this one, and so on. They're not all going to be uniform. They're going to be a little bit separate. If you change the scale of time, that plot ends up looking like this. It looks like a stair step. These are not really steps. They do change a little bit with respect to time, but if you turn down the resolution of your measurement device, you will find that it looks an awful lot like a stair step. So we have water inlet temperature down here. We have air return temp, or a crack air return temperature here in green, and then here is the water return temperature. So that is what it looks like when you look at it as a longer function of time and a longer scale on the temperature. So the point is that you begin to do this analysis and you do these steady state cases. We did one at 33. Here's another one at 41. Here's another one at 49. Now we actually did them at a second apiece, I think. We did quite a few of these. But the point is that to get to 90 Fahrenheit, it didn't occur until we got into this simulation fairly long. And then what you can do is you can see in particular which servers are getting hot. You notice we've got some issues down here in this lower right-hand corner. We knew we would. We've also got some issues over in this section of the room here. And then we keep going, 81 seconds, and we find out eventually that the temperature gets to a certain point, and we want to know where that is. As it turns out, here it is, and then we spun this image around, so I'm looking back at it again compared to how I was. This is how it was before. I spun it around and looked, and we see right here we've got these racks that are being heated up first, and those are the ones I need to worry about. This is important, by the way. It took 120 seconds to do that, 129 seconds. So you've really only got a couple of minutes in this particular scenario to affect this situation. And if you're an IT person, what you know is these are the servers or the racks that are most vulnerable to this kind of failure. And therefore, in your failure mode scenario, what you'll want to do is you want to figure out a way to start drawing the data out of those servers as quick as you can, because those are the ones who are going to go up in smoke at some point, and you're not going to be able to solve that problem. Okay. So there are many modes that can be modeled using straight steady state kind of methods. There's DX-based system designs that, N+1 that work very, very well because you're going to lose one of them at a time. There are systems with redundant backups that could be chilled water, but you've got a backup system, battery backup system, and followed by generator for the air handlers in the room. And generally, you also have that with the pumps and with the chillers. In those cases, both these cases, this is just a simple steady state N+1 kind of design. In other words, you just turn off the DX unit, do a run, turn off the next one, do a run. Same thing with the air handlers, turn one off and do a run. N+1 analysis is typically done of all data center designs that we work with and that our customers and many of you work with. Understanding what happens when an air handler is down or a DX unit is down is very important, because depending where it is, it'll have a dramatic effect. It's not sufficient to just assume that you have enough cooling capacity and you're all set. You need to know where the cooling is. Geometry makes a difference. For chiller failures, specifications of the cooling system are really important. You need to know the amount of water, you need to know the flow rate of the water, and then what you can do is a CFD run for each one of those time steps. Effectively, what's happening is your cooling capacity is declining with respect to time as a function of the amount of water you have in the loop. So all you need to do is figure out when that hot water that hasn't yet been chilled comes back, and then you can effectively change the cooling capacity of the air handlers in the room. This is also the same case if you wanted to bypass the chiller and go to the cooling tower. Same exact case, a ramp would be different, because going to the cooling tower or some other device will change the rate of increase. And it's even a function of depending on the time of year. If it's winter time and you're using a cooling tower, maybe you don't need to worry about much because you've got enough cold out there. You've got an infinite sink, effectively, of cold air to dump the heat to. These things will all affect the transient analysis of the data center. So it becomes more of a systems approach, a systems analysis to be able to figure that stuff out. Now, with respect to the other conditions where you have a chiller fail, then you can go ahead and just run it that way. And what these can do for you, what these models can do for you is allow you to optimize those conditions. In other words, in a failure mode condition, what is the best thing I can do? In some cases, what I've seen people do is open the doors of the data center and put in portable fans, portable cooling units. That's okay if it's not contained. If it's contained, you might have trouble with that approach, particularly if it's cold out contained. That's not going to help you. Some other things that are possible to do is to change the plumbing configuration in a failure mode. In other words, I told you that oftentimes they bypass the chiller with a plate and frame heat exchanger to absorb some of the, or reject some of the heat to the outside atmosphere. You can do that as well, and you might want to go there as a failure mode condition and dump as much as you possibly can. Those can all be simulated using the same methodology that we've described today, and you can therefore optimize for a failure mode condition and know exactly what to do and set up the logic for your control system to be able to go do that. Not a problem, easy enough to do, and using these methods is a way to do that. So I just wanted to take you through that quickly. Just to summarize, I'm going to open it up for questions in a moment. So if you have questions, and I see there's a number here of questions, I'll start to go through them. These tools are complementary. They're looking at, they both can do transient analysis. The point is they're looking at a different level of granularity. IcePack is focused within the package. Jim meshes inside. He meshes the volume inside that package. He's dealing with radiant heat transfer. He's dealing with conductive heat transfer, conjugate heat transfer. In the data center, it's primarily convective. So at CoolSim, I only deal with convective. He treats his electronics package itself, all the geometry in it. He meshes inside these building meshes that are multi-million cells using the same exact mesher that we use on the data center. It's just an issue of granularity. We're focused on the data center at more of a macro scale than IcePack, which is focused inside the box itself. But the transient methodologies are the same. We use the same exact meshing, same exact solve, same exact post. The level of detail will change. Now, over time, that will evolve. I'm old enough to know this because I've seen it happen where the level of detail will continue to increase. For example, Jim in his slides talked about reduced order modeling or submodeling. This is the idea of modeling inside the package first and coming up with effectively a polynomial, an algebraic representation of what happens to temperature as a function of time. At the end of the day, you're interested in knowing what's happening to temperature as a function of time. That can be, once it's modeled, it can be expressed algebraically with a simple nonlinear polynomial representation and used in a more coarse granularity package like CoolSim as a representation of what's going on inside that package. So in other words, the user-defined functions we use for defining what's going on inside the rack or server within the data center model can be refined and simulated and discovered effectively by using IcePack, and then those models put into CoolSim for representation. And I think you'll see that over the next few years. In this way, you can get more and more detail into CoolSim, more IcePack detail into CoolSim, and be able to handle more cases. It's a simple evolution of time. It is, when I talk about practical considerations here, I'm talking about compute time and the amount of data. The compute time, remember, for a mesh that is 10 or 20 million cells is going to be a few hours. And that's when running it in parallel on a cluster like we do with CoolSim. So you have to be practical with respect to your expectations about what can be done. Having said that, over time, the fidelity has been increasing and simply going up. So you can expect more of it tomorrow than, in fact, you saw today. So with that, I'm going to open it up for questions. I did want to leave enough time for questions, and we are running on time here. So the first question I think I answered, is it possible to do a transient CFD analysis in a site that uses both DX and fluid at the same time? The answer is yes. I mean, the DXs are fairly easy. They're on-off. So if you lose a DX unit, the liquid-based system has to absorb all of that extra heat and you're going to see some there's gradients, some temperature gradients in that room as a result of that failure. So the answer is yes. Now you can go the other way as well, and you can drop out the cooling side and let the DXs handle it by itself. So mixed mode's not really an issue, it's just a knowing what they are. So the next question is it possible to do a transient CFD analysis on a site that uses a DX and dual fluid evaporator solutions at the same time? A little more difficult. That is a situation where you've got both mediums in the cooling unit. This often happens. They put gas in there. They also put liquid in there. It's in the box, inside the unit, in the room. Again, all you have to do is decide which one you want to fail, if you want to fail them both. The DX, again, is fairly simple. If it fails, the game over. If the chilled water fails, then, are the pumps running or not? Same set of questions. Effectively the same scenario that we just talked about. Elaborate on the thermal control options. There are many. Fan flow during total failure, yeah. I mean, there are many conditions that you need to consider. The complexity in particular of a chilled water cooling system and its various control logic that runs it is something that needs to be studied in detail and understood when doing transient failure study mode for a chilled water-based system. Control logic has a lot of importance here because it depends what resources are at the site. It is not unusual to find they have a reservoir of water, for example, that they can use. I have one customer who has an underground aquifer that they can draw on. So that's a kind of an infinite heat sink to draw upon that they use most of the time. They don't compress very much at all. They only compress once the reservoir has gotten to a temperature they can no longer use. Then they'll start to use a compressor. So failure mode for them is pretty easy. It depends on the exact configuration that you're looking at. Is transient analysis available in CoolSim directly? No, we don't have it in there because it requires right now quite a bit of investigation to know what's going on inside. And CoolSim is a steady state, set it up, let it go, forget about it until the results come back kind of approach. With transient, you often have to see if your time step is correct and if your convergence is good before you can take the next step, or at least you want to take a look at those factors as you pass through time, simulation time. So adjusting the time step so it's correct and getting the residuals or the convergence good enough is always something that's important to do. That historically has been done with a person in the loop, so to speak, a man in the loop, who looks at those outcomes and makes sure they're palatable or sufficient before proceeding. So we haven't quite exposed it yet, but we probably will do that in the next year or so. So here's a question: how the air on the inlet of the rack is modeled? Is it uniform? Does it vary with time? In CFD, we model it just the way it is. It does vary with time. It is non-uniform. So the air inlet on the front of the racks is non-uniform. That's the value of CFD, is modeling the entire gradient of air in the room. It can be as a function of time. It usually resolves to a steady state condition, however. So we generally do it in steady state. Is the IT fan flow simulated during failure? You can simulate the IT fan during failure, yes. You can do it in a variety of ways, but we aren't right now ramping those fans down as a function of time because we're just assuming they're going to zero fairly quickly, and they do go to zero fairly quickly. Studying the effect of the thermal condition during the ramp of the fan from full speed to zero is of some interest, but in the general case, it's not going to matter all that much with respect to time. Yep. So with that, we're running a little earlier than I thought. Jim, any thoughts? Anything else you'd like to say?
No, nothing. I did see in the chat something here that said question for Jim, but I didn't hear anything beyond that. So if the end user would like to contact me offline or elaborate here, that'd be fine. Otherwise, glad to help and provide any further information on either IcePack or any of the other tools in the Ansys platform.
Just a question for you with respect to IcePack. I'm assuming that in the transient case within IcePack, your heat transfers are all valid. In other words, you're going to consider radiant as well as a function of time, a conjugate heat transfer, the whole thing,
Yep.
right?
Yep. Everything is taken into consideration.
And a lot of your work is handheld devices that don't really have much convective. So your ability to model radiant loss, I know in items like cell phones, most of the heat transfer happens through the case.
Right.
So they're depending on that case to be able to reject the heat, and then of course people put them inside of these plastic devices to keep them from breaking, and it reduces the ability to do heat transfer effectively through the back of that device. It must be a challenging area.
And as we get further into 5G and the power densities increase dramatically, we're seeing that problem just exacerbated. So, and that also extends to the data center side too. As we move towards 5G, there are going to be a lot more edge centers created that are going to most likely have higher power densities and or energy densities, and the cooling scenario in all of those, whether it's from the case up to the rack, all the way up to the data center, needs to be considered.
Yes. There is a little bit of a lull right now in terms of thermal pressure in the data center, Jim, caused by virtualization and the lowering of power consumption on the part of the microprocessor manufacturers. Virtualization has allowed the number of boxes to be consolidated to a smaller group, and there was an awful lot of fluff, so to speak, in that system. Here I'm talking thermal fluff. In other words, the density was distributed out over a larger number of units physically. With virtualization, it brings it all to one box, one higher density box, one higher density server. And for now, that's okay. What I'm being told by some of my data center users is density isn't a problem right now. But it will be over time because the march of data doesn't cease. It continues to increase exponentially, and the amount of information processing we're doing goes with it. So what I expect is we've seen a flattening of the curve of thermal problems in data centers to be followed by another ramp that will come, as you point out, as we get to things like edge data centers. You agree?
I do. And also, just looking in the chat window too, it looks like the user had asked to elaborate on the fan thermal control options. I'm assuming the ability to control fans within IcePack.
Yes.
And to go into that just a little bit further, we do have a mechanism in place where you can vary fan speed versus time within the individual box simulation. And we do have some amount of control. There is a thermostat capability within IcePack that allows you to do some level of control in terms of adjusting the fan speed based upon temperatures monitored within the simulation. So we do have some of that capability built into the tool itself.
Now, at the moment in CoolSim, we do not do that. The amount of airflow through the server, through our server, is really a function of load in the server. It's that simple. You know, it's a roughly 156 CFM, around 100 CFM per kW, and we assume a linear relationship. Good enough for most situations. However, most of us do agree, and sort of in general, that when you get up around 77, 78, 80 degrees, these servers will start to ramp up in fan speeds. And when they ramp up in fan speeds, the energy consumption goes up according to, a cubic relationship and fan law problem. Furthermore, the amount of air required goes up with it. Your experience, Jim, that function, although we could model it in IcePack and we could write a reduced order modeling for CoolSim, but that relationship is pretty much proprietary, isn't it? I mean, it's up to the manufacturer to come up with their own thermal control system, and I suspect they hold that knowledge pretty close to the vest. Is that true?
Yeah, that is true. And as a matter of fact, we're seeing a lot of manufacturers going to significantly more sophisticated control algorithms, and that's an area of optimization in and of itself. So we're seeing a lot of people saying, okay, we want to design a box and we have to look at that box with 12 fans spaced around the inside the unit, and we have to implement some kind of algorithm to control all of them in the event of certain failure modes, whether it's from chips or whether it's from power supplies or whatnot. And yeah, that algorithm in and of itself is becoming incredibly complicated. And I'm not saying that we have the ability to include that software level of control inside of IcePack. We do have some basic ability for thermostat control within the simulation, but as you mentioned in your final slide there, we're marching toward that capability where we're going to be able to generate larger and larger reduced order models for these units, can pass them up to the data center modeling and do more sophisticated control of the individual fans within the boxes. So we are seeing a lot more application of the basic technology for some of these more complicated systems.
Yes, yep. And it will get more complicated. I mean, today in the data center alone, we have multiple control systems. We have a control system, usually thermostat driving the fan. Oftentimes there's underfloor pressure monitors driving the fans. There's a thermostat driving the cooling valve, the chilled water valve in the air handler itself. And as you just pointed out, there's a control loop inside the server itself. These can't compete against one another and they can oscillate. So our challenge over time for the both of us is create a solution that that doesn't oscillate, right? Because these things can interact with each other in a negative way. And I witness this in data centers when I visit them. You walk in a data center and you'll hear, a server go from a moderate fan speed to a high fan speed and then back down and then back up. It sits there and you're in the data center and this thing's ramping up and down because the control system for that particular unit is oscillating. And trying to model that in a data center is going to be challenging because we try to model things as steady state, but again, it's not. The world is really a transient situation. So the long and short of it is you have to make some approximations. You have to make good engineering judgments. Simulation tools in general, like the ones we're describing, help you make good engineering discussions. They're not a substitute. They're just there to help us make better decisions, more informed decisions, by allowing us to understand what parameters are important or not. Level of detail is up to the individual user. At the moment, we can define CoolSim with a rack that, a rack, an IT rack, all the way down to a single U, one U, which is about 2.75 inches and we can put a function on it. The function we put on it at the moment is a linear function based on load. In other words, it's fixed. Will that be a variable in the future? Yeah, we can make it a variable. Will it increase the overall instability of the total simulation? Yes, it will.
There's no free lunch.
There's no free lunch, and we're going to have to deal with that. But again, it'll happen over time. We will deal with it, and we'll figure out how to get these control systems to behave themselves or tell the user that it's not behaving itself and it's oscillating. But these things will come. The great news about this partnership with us is that for CoolSim users, we don't here at Applied Math Modeling have to reinvent all that stuff. In other words, we get to take advantage of the work that's being done by the Ansys Corporation. And with respect to market, data center market is really too small for a company of Ansys' size to pursue themselves. And so using partners like us allows them to take the base technology that they've just spent a lot of money developing it and amortize it across, in this case, a niche market from their point of view in terms of size, which is data center design optimization. So that works good. It saves the customer money because I don't have to go reinvent the wheel here. I can take advantage of your technology. And at the end of the day, what's inside of one IT server is no different functionally than what's inside one big data center, except for scale. I say that with a little bit of freedom, literary license, because I'm not considering radiant heat transfer not a big deal, usually in a data center. Conductive heat transfer, usually not a big deal either, although both of them are becoming more important over time. With exit temperatures now 120, 130 degrees Fahrenheit coming out of these servers, they are beginning to radiate heat a little bit, and conductive does make a little bit of a difference, although not a whole lot. So over time, I expect we'll be exposing those levels of heat transfer in the package as well. So I think that gets us to the end of our time here in our webinar. I'd like to thank Jim for being here, and also Abhishek. Abhishek, I'm hoping that I was straight there and kept our audience honest, or they kept me honest. I don't think there's any questions
Yes,
there
you were very good, Paul.
that I wasn't able to answer. And for those of you in the audience, if either one of you would like to ask us follow-on questions or get in touch with us about any of these things, please feel free to do so. Our email addresses are posted here. Jim, thanks for the webinar today, and I look forward to working with you in the future.
Thank you for the opportunity, and hope everyone has a great day.
Thanks. Bye.